So probably we'll start out with something like this. Find the derivative if y equals, oh, I don't know, 7x to the fourth minus 3x squared plus 2. What's y prime? So the first thing that you've learned is if you have separate terms, you don't do the entire derivative all at once. You can go term by term by term. We learned that if they're separated by plus signs or minus signs, it turns out you can do the derivative one term at a time. So what's the derivative of 7x to the fourth? This is what we call the power law. What was that one? You multiplied the exponent onto the front, rewrote what was inside the exponent, and then you subtracted 1 from the exponent. And then technically, although you didn't realize it, you were doing the chain rule, because the chain rule always says this. Do the outer rule, which is the power rule, rewrite what's inside, the x, times the derivative of what's inside. This is technically times the derivative of x. But you know what the derivative of x is? It's 1, so we never bothered writing it. But believe it or not, you've been doing the chain rule the entire time. The chain rule says start on the outside, do the derivative rule for the outer function, rewrite what's inside, times the derivative of what's inside. Lather, rinse, repeat. Lather, rinse, repeat. Just keep going over and over and over until eventually you end up with the derivative of 1. You're done. You okay with that one? Okay. So I wasn't getting any feedback from you at all. This one I'm hoping you can kind of do it not in your sleep. But minus, then what? What's the next term?
6.
And then what's the derivative of a constant? Technically, plus 0. Do we bother writing the plus 0? No. Okay. I'm willing to bet that'll be your first question, or one of the first questions. It's the basic derivative, the power law. Kids like that one. It's so much easier than using the limit definition. I don't think he's going to make you do the limit definition, but you want to find out. If he does, ask me and I'll go over that tomorrow in Flex. The product rule. What's the product rule? The product rule says if you have a function times a function. The product rule is on your formula sheet. I was never good enough to do this in my head. I would write stuff down and make notes. But, Karen, as always, lazy but organized. I would say to myself, that's U, that's V. The notation that we use, I think, on your formula sheet is U for the first function and V for the second function. And the product rule says this. UV prime is the same as U prime V plus UV prime. Or they might have flipped the order. It's the derivative of this times leave that alone plus leave that alone times the derivative of this. So, here we go. Y prime would be the derivative of this, which is 4x to the 1 plus 4x. Leave this alone. Plus, leave this alone. Times the derivative of root x. I never did the derivative of root x. I always turned that into an exponent. Because now I could use my power law. What was the power law? Move the exponent to the front, rewrite what was inside, subtract 1 from the exponent. And I found talking to myself, having a little internal monologue like that as a coach really helped me. You're going to see it's going to come out when we do these. I'm going to talk my way through it, especially when we get to the chain rule. Probably they wouldn't leave it like this. A negative exponent, I always taught my students, it acts like an elevator. It will cause this x to change floors. This will become 4x root x. Well, they might write this as x to the 1, x to the 1/2. And then they might say, well, your bases are the same. You can add the exponents. 1/2 plus 1 is 3/2. They would probably, if this was multiple choice or in the back of the textbook, write this first term as that, because that's what it simplifies to. Then plus, leave that alone. They would probably put the 1/2 in front. But now what I've really done is I've said there's a 1 on the top and a 2 on the. And really what I've done is I've implied that there is a fraction there. And x to the 1/2, that's the same as x to the positive 1/2. A negative exponent will cause a number to change levels. It was on the top, now it's on the bottom of the fraction. Except what's a better way to write x to the 1/2? They'd probably write it as that. And one of the challenges and one of the things I didn't like about the textbook that we got was there was no clear guidance. When do I stop simplifying? And so what I'll tell you, if it's a multiple choice test, every time you do a step, stop, go look at all your answers. You might be done. No, keep simplifying, but don't simplify until the cows come home. Check on the back of the book, keep simplifying until your answer matches the one on the back of the book. The other thing I didn't like about this textbook is they only had the answers for the odd-numbered questions. I'm old school. I'd rather have them all. Well, such is life. Okay. Is that all right? Nothing new there. What does that mean? F double prime. What does that mean? Okay, second derivative. Okay. I usually ask the question where I ask them to find the second or the third derivative. It was almost always a trig function or something with a big exponent that would continue. Find the second derivative of 3x to the 12th. That you can find the derivative of 3 times. In fact, you can find the derivative 12 times before you run out of exponent. Okay. So what is this? What is the first derivative of y equals cos x? Now you should either know this or you should be looking at your formula sheet. I'm sure it's on your formula sheet. What's the derivative of cos x? So the first derivative would be negative sine x. What's the second derivative then? The negative is going to stay where it is because it's really a negative 1. Derivative of sine x. Of course it is. Third derivative, that would be negative sine x, although how would we probably choose to write that? Yeah, I'm positive. Okay. So there's probably going to be a question where you do what we call higher order derivative. That would make sense to me. You should know that. We just got way tougher. This is a product rule. That's U. That's V. I know the product rule says this, UV all prime is U prime. Does he write U prime V and then VU prime, or does he write, which one does he write first on his formula sheet? I got it in front of me, duh. U prime, okay. Doesn't matter, but I would probably actually evaluate these. I mean, I know what V is, it's cos x. I know what U is. Sorry, I wrote this down wrong. What is it? U prime V plus, you wrote it down wrong. V prime U, or UV prime. That's how he wrote it on a formula sheet. Okay. What is U prime? What's the derivative of sine squared x? This is a chain rule. What's the major function? Squared. That's the outer function. How do you take the derivative of squared? Move the exponent to the front, subtract 1 from the exponent. Rewrite what's inside, which is sine x, times the derivative of what's inside. What's the derivative of sine x? This is the chain rule. The derivative of sine squared x is 2 sine x cos x. What's the derivative of v cos x? Oh, negative sine. You all just told me. Now I would carefully do the substitutions. So apparently this y prime is going to match this template, u prime v plus v prime u. So what's u prime? 2 sine x cos x. V cos x. Although, what's a better way to write cos times cos? I guarantee they would write it like that. Then there's apparently a plus sign. V prime, u, v prime, negative sine x, u sine squared x. Although this is like a times a squared. What's a better way to write a times a squared? A cubed? What's a better way to write sine x times sine squared x? Okay? And you've learned enough trig to know that we put the cubed there to show that it's not the x being cubed, it's the sine of x all being cubed. Then probably they would just put a that minus that. Okay? What else could we do to simplify? Well, there's a GCF of sine that maybe I could factor out, but I'm just not sure why I would. Okay? So that's an example of chain rule and product rule combined. Quotient rule. A little yuckier. I'll be honest, I often turned a quotient rule into a product rule. Let me give you an example. If you asked me to find the derivative of I would probably write this as and now it's a product rule, because I was good at the product rule. I would use a negative exponent acts like an elevator. I would say, well, x to the 2 on the bottom is the same as x to the negative 2 on the top. Now, I don't know how good you are with negative exponents. I was pretty good at it. And then I would do exactly what I just walked through here. I would write out u v all prime equals u prime v plus v prime u. I would literally write out everything. What's v? What's u? What's v prime? What's u? And then write my answer down here. That was my cheat. What if they said you had to use the quotient rule in your work? Well, quotient rule. I guess that's u. I guess that's v. And the quotient rule says what? U over v prime is, I'm reading, u prime v minus v prime u over v squared. U prime v minus v prime u over v squared. Any of you getting 100% in calculus right now? If you're not getting 100%, don't try and do these in your head. Write out your steps. I know what v is, x squared. I know what u is, cos x. What's u prime? What's the derivative of cos? What's v prime? Okay, now I'm going to plop that there, but with all the substitutions. Here we go, Karen. Y prime equals u prime negative sine x v x squared. They would probably put the x squared in the front like a coefficient, but I'll write that for now. Then there's a minus sign By the way, if I make a mistake, please holler at me because it's been a while since I've done calculus. V prime, 2x, u cos x, all over v squared. What's x squared? Squared. Here. There's a little bit of simplification we could do. Is there an x hidden in the first term? There's an x squared, but is there an x hidden in the first term? Yeah. Is there an x hidden in the second term? Yeah. Is there an x hidden in the bottom? Yeah. You can factor out a single x and cancel it. Okay? Have I made a dumb mistake? Are you guys okay? I'm doing good so far? Who knows? So you could take this one step further. You could go factor out an x, and on the top I'll have negative x sine x. I move the x to the front because that's where you'd normally write it. Minus 2 cos x all over x to the fourth, and that x would cancel out one of those. That would be your final answer. Chain rule. Ready, Nasiba? I found for me to do the chain rule, I had to talk myself through it. Okay? What's the chain rule? It says this. Start on the outside, do the derivative of the outside, rewrite what's inside, times the derivative of what was inside. Repeat. Let me show you what I mean. What example am I on now? 6. Y equals sine cubed of bracket 3x to the fourth minus 2x. Okay. What's the outer function? Yep, cubed. Okay. So the first thing that I'm going to do is do the cubed rule, which was move it to the front, subtract 1, rewrite what's inside. My 2's in a bad location. I'll put it there. And what I would often do on the original question is say, took care of that. I would cross out what I've just taken care of. What's the next outer function? Sine. What's the derivative of sine? Rewrite what's inside. Times the derivative of what's inside. I think. Oh, technically times 1 after that, because. Okay, so let's walk through that. Did that work? Take care of the cubed, rewrite do that, rewrite what's inside, times the derivative of what's inside. What's inside? Sine of that. So, sine, cos, rewrite what's inside, times the derivative of what's inside. That's the chain rule. Is that right? I think that's right. Or have I done it wrong? Prabner's looking at this like I've done it wrong. Maybe I have.
I know.
Let me pause the video for a second. That's probably tougher than Mr. Camosi's going to ask you. That's tougher than what I had on my old test. But that's a chain rule, and I talk to myself. Okay. Someone asked about differentiation. differentiation. I can't even spell that. Besides, but I think you had asked about implicit. Oh no, you wanted implicit. Okay. Again, implicit differentiation is something that you've been doing sort of all along. But here's what it says. What if you can't get the y by itself? Well, take the derivative using the chain rule and see if you can get the y primes by themselves. So here's a great example. Example 1. Okay. Is that big enough? You can all see okay? Okay. How can you tell it's an implicit differentiation question? The y isn't by itself to begin with. That's probably a good sign. And you can't easily get the y by itself. All right. So here's what I'm going to do. I'm going to take the derivative implicitly. And what does that mean? First, I'm going to take the derivative of 2x cubed using the power law. That's going to be 6x squared, technically times x prime, except what's the derivative of x? But believe it or not, you've always been deriving implicitly. You've always actually been doing that extra step. It's just because it was a 1 we never mentioned it. Okay? It's always been do the derivative on the outside times the derivative of what was inside. What was inside? An x. What's the derivative of x? X prime. What's the derivative of x prime? You have to know that. Okay. So we normally don't bother writing that. I'm going to leave it there, though. That's a 1. Use the power rule here, too. 4y, subtract 1 from the exponent, times the derivative of what's inside. I'm going to get rid of that 1 because we never write it, but it's there. Plus, what's the derivative of 5?
0.
Okay. Get the y prime by itself. Oh, this, by the way, is just a 1. But can you see, it's kind of what you were doing with this. It's just that here, because I know y is a function, y prime is not a 1. So I can't just ignore it. Because I know x is just the variable, I know the derivative of x is 1, so I've always been able to ignore it. But that's always been there invisibly without me realizing it technically. How would you get the y prime by itself? Then, if you're lucky, they'll give you an x and a y that fit on this graph. You can plug them in and actually find what the derivative is, what the slope is at that specific location of whatever weird graph this is. This can simplify a little bit, by the way. They'd probably write it as that, right? That's implicit differentiation. How do you know it's there? The y is not by itself. Take the derivative of each term one at a time, and whenever you take the derivative of a y thing, don't forget to tack on the y prime. Technically, you should always tack on the x prime, but what's the derivative of x? What is x prime? Just plain old? Forget it. But we can't make that assumption with y because it's a function. Why is it called implicit? Because you're not actually taking y prime. You're finding it somewhere in the rest of your function, and you're getting the y prime by itself. But you're not solving for y prime explicitly like we did up here just by getting it by itself. Let's do another one. Okay. Ooh, here, 6. I can tell right away. Y is not by itself. Implicit differentiation. Then we'll try 8 that's got multiple y's. Cool. Here we go. What's the derivative of 1? That's easy. What's the derivative of 3x? Technically times x prime, but x prime is just 1, so what's the derivative of 2x squared what? Product rule. Okay. And again, don't be scared to make notes in the margin. Even in my prime, when I was good at calculus, I still did this. And then I would say to myself, okay, u is 2x squared, v is y squared. U prime is 4x to the 1, technically times x prime, but the derivative of x prime is just 1. V prime is going to be 2y times whatever that derivative was. Here we go. Plus u prime, 4x, v y squared, plus v y squared. No, geez, Dewick, I did it again, didn't I? V prime u. I can't even remember the product rule. V prime, 2y y prime times u, 2x squared. 2 times 2, you know what they would turn that into? So let's write this tidier. Also, you'll notice I'm not taking many shortcuts. Physics, yes, I'm very meticulous in calculus. The 3 is going to drop down. The 4xy squared is going to drop down. I'm going to write this as a 4, and then I'm going to put the x squared there, and then I'm going to put the y there, and then I'm going to tack on the y prime. That's what I want to get by itself. Luckily for 4 of you, you're good at formula manipulation. One poor schmuck didn't do physics, and so maybe is not as good as formula manipulation as the rest of you, but I'm pretty sure minus the 3, minus the 4xy squared, and then divide by the 4x squared y. I think it's going to be a negative 3, a negative 4xy squared, and then divide by a 4x squared y. That equals y prime. Is that right? Yeah. That's implicit differentiation. Where it gets a little trickier is when there's more than one y, because then you're going to end up with more than one y prime. Ready? You might even see that I planted a calculus seed in physics on purpose because I knew that some of you might be seeing something like, oh, number 8. Find y prime. Okay. The first term is easy. Decide about what's the derivative of 5x cubed. Yeah. Technically times the derivative of x, but that's just 1, so who cares? We know it's not a function. Ooh, product rule. All right, let's see if we can maybe just do this. No, never mind. So the derivative of xy squared is going to be u prime v plus v prime u. That's how I always wrote it. U is x, v is y squared. So what's u prime? What's the derivative of x? Yep. What's v prime? 2y times y prime. Okay, so I'm going to need more room, and I'm going to change colors. I'm going to do this one in red. So we had 15x squared, and then it's going to be plus u prime v. Technically, 1y squared is the one going to make a difference. Plus v prime u equals another product rule. The derivative of 5x cubed y cubed, that's going to be u prime v plus v prime u, where this time u is 5x cubed, v is y cubed, u prime is 15x squared, v prime is 3y squared y prime. Gonna need more room. Ah, the beauty of digital ink. Now I have more room. U prime 15x squared. V, y cubed, plus v prime, 3y squared y prime, u, 5x cubed. Let's tidy up coefficients and stuff. Really, the one that I see that can be tidied up is the 3 times 5, which is the 3 times 5, which is, okay. So this can all be written as 15, that term's good, that term's good, that looks okay. I mean, honestly, because we write things alphabetically, 2x, y, y prime is probably how they'd write that. 15x squared, y cubed. Again, if you see me make a dumb math mistake, holler. Plus, and they'd probably go 15x cubed, y squared, y prime. What am I trying to find? How many y primes do I have? How many would I prefer? Get them to the same side. This one's yuckier. I'm going to keep it positive. I'll minus this here and minus that there. Also because there's 2 terms there and I'm lazy. You can also see there's a lot of potential to make a copying error, a transcription error, to make a sloppy mistake. So you really got to raise your game. How many y primes do I have? How many would I prefer? It'd be really neat if there was a Math 9 operation that I could pull out of my back pocket and change this from 2 y primes into 1. Do it? Is that why you snuck that in calculus? Maybe. What? GCF. There's a y prime in both terms on the right. I can write this as 15x squared plus y squared minus 15x squared y cubed equals y prime bracket 15x cubed y squared minus 2xy. Finn, they saw that little dance in physics when we were doing a specific type of question. And I hope that I gave that I added that to your mathematical toolbox. Because now, how will I get the y prime by itself? Divide what? The bracket over. Now, this is an ugly derivative, but if you told me what x and y were, I could go to my calculator and tell you what the slope at this location was. Here it is. And again, I don't think you're going to get one this tough on your test. This I knew as soon as I saw multiple y's and all those exponents. This is going to be a deep dive here. It's going to be 15x squared plus y squared minus 15x squared y cubed. Assuming I haven't made a silly math mistake, and YouTube will scream at me if I post this and I have done a silly math mistake. Thank you, YouTube. I'm pretty sure that's the derivative. All right? Logarithmic differentiation. How do I know when to use logarithmic differentiation? The x is an exponent. That's how you know to use logarithmic differentiation. Got an example of some here? Yeah, there we go. Look at that. Do it. Let's try number 2. How do I know I'm going to use logarithmic differentiation here? X is an exponent. Logarithmic differentiation is kind of exactly what it sounds like. You start out by taking the log of both sides, except you don't. You take the natural log, the ln, or we used to call it the ln of both sides. That was our little abbrev, okay? Why the natural log? You're starting to see because it gives you way cleaner derivatives. right? Base e has a lovely derivative. What's the derivative of e to the x? E to the x. Right? Okay. So, I'm going to go ln of y equals ln of 5x to the 5x. Why does that help? Well, now I can use my log rules. What can I do with that exponent? What can I do with this? Move it to the front. To ground level. Because we have no math that can deal with solving for an x when it's an exponent. Once on the ground level, not a problem. That's going to turn this into ln of y equals 5x ln of 5x. I kind of wish this 5x and this 5x weren't the same. I would have made up different numbers so I don't confuse them. 2x and 5x, but that's what we got. Now what? Now I'm going to take the derivative. It's going to be an implicit differentiation. Because I can't get the y by itself. I could here, but the problem with that was I don't have any way to take the derivative of the x when it's an exponent. So what was the implicit differentiation? Here we go. What's the derivative of ln of x from your sheet? Front page. Under other differentiation formulas, just past halfway down on the right. Karen? What's the derivative of ln of u? Because y is a function. 1 over u times u prime. Okay? 1 over y times y prime. We never write it that way. We write it that way. It's y prime over y. Okay. Product rule! Yay! U prime v plus v prime u, where u is 5x. So what's u prime? V is ln of 5x. So what's v prime? 1 over 5x times the derivative of 5x. Right? Is that right? ln of u, that's that, is 1 over u prime. So 1 over 5x times the derivative of 5x. Oh, that's why they had those two numbers the same, because you end up with just 1 over x. I see why they did that. They're making up a nicer question. So what's the product rule? U prime. V. Plus v prime. U. You know what? When you're multiplying, that means it just ends up on the top. Ooh! Okay. So I end up with this. Not done yet, but okay. Your log rules, you may remember, say when you're adding, that's the same as multiplying. Is this the same as multiply? No, because this is not inside a log. I can't use any log rules with that 5. I could move this 5 back up on top of the 5x as an exponent, and I might. But first, what am I trying to get by itself? Oh, how would I get the y prime by itself? How will I move the y over? Okay. So this is going to look like this. Y prime is equal to y bracket 5 ln 5x plus 5. Yes? No. I can do one more thing. You ready? What's sitting right there? What letter? Do you know what y is the same as? What can I replace a y with? Instead of that y, I'm going to put a 5x to the 5x right here. That would almost certainly be, if this was a multiple choice test, their final step. They would say, well, get rid of the y. Why? Because I asked you to. Okay. Get rid of the y. So y was 5x to the 5x. So I can write this as y prime is equal to 5x to the power of 5x, that's one big bracket, times 5 ln 5x plus 5. Whew. That's logarithmic differentiation. It's tricky, but what's your trigger? If the x is sitting where? Exponent. Take the log of both sides. You'll have a y prime, and now it's implicit differentiation, which is why we always do logarithmic differentiation after we've done implicit differentiation, because it's a special subcase of implicit differentiation. Get the y prime by itself. Okay? That's all the derivative rules that I think you have done. Oh, trig one. Are you okay on the trig ones? Derivative of sine is cosine. By the way, isn't that a lovely answer? I remember smiling when I learned that, because it could have been such an ugly answer and the universe saying, "No, I got your back, Jack. You want derivative of sine's cos." It would have been nicer if the derivative of cos was sine, but even negative sine, not too big a deal. I kind of like that. Then you have all these. So you're at a bit of a disadvantage because you haven't done, I don't think, trig identities the same way most Math 12s have. I suspect, who had pre-calc first semester? Did Mr. Gerard do a whole bunch of trig identities, sine squared plus cos squared equals 1, bunch of trig identity practice? Okay. So you're at a disadvantage. Normally people coming out of Math 12 would have almost inadvertently, through sheer repetition, memorized most of those. You would have done a whole bunch of they're math puzzles where you would be given a really complicated trig expression and they would say, prove that it's the same as this other thing, which is way simpler. And you would say, well, there's a sine squared. I can replace sine squared with 1 minus cos squared, because if sine squared plus cos squared equals 1, then 1 minus cos squared is the same as sine squared. What else can I? And you would just start substituting a bunch of stuff and being careful with your fractions, and all of a sudden stuff would cancel. Okay, good. I was able to make one side equal another side. You're at a bit of a disadvantage there. So that whole reciprocal identities, quotient identities, Pythagorean identities, addition formulae, and double angle formulae, I doubt Mr. Camozzi is going to be asking you or doing much with that. But at the very bottom, the derivatives of the trig functions and the inverse trig functions, arcsine, arccos, and arctan, those are fair game. But they're kind of plug and chug. I mean, careful, but it's there. Tangent lines and normal lines, are we okay with those, or do you want me to do one like that? Did he say whether there's going to be tangent lines and normal lines? I know you had them on your limits test, and then you learned, it's way easier to do it with derivatives than the long limit definition, right? And it's a nice application. Do you want me to try and make one up? Reading it? Okay. Let's see here. Just trying to look at some combinations of. Okay, so before I go further, a few more derivative rules. What was that? You can allowed to speak out loud and ask.
Is that?
Did I make a dumb mistake?
No, is it just square bracket and then round bracket?
Because
or is it like
I was inconsistent. No, that's a great question. I was inconsistent because I was trying to differentiate brackets to make it easier to read. And it's funny because I even remember thinking, why wouldn't I put a square bracket at the front? And somehow I must have looked elsewhere, or I looked at that or something. I don't know.
Okay.
You just organize your brackets a little bit. Okay. Just again, some more weird derivatives. If y equals, I don't know, e to the cos 2x. What's the derivative of e to the x? E to the x. What's the derivative of e to the u? I think it's e to the u times the derivative of u. It's a chain rule. Okay, so this is e to the u. E to the u equals prime equals e to the u times u prime. What's u? I guess cos 2x. So what's the derivative of cos 2x? Chain rule. Start on the outside. What's the outer function? Cos. What's the derivative of cos? It's going to be negative sine, rewrite what's inside, times the derivative of what's inside. What's the derivative of 2x? And this might be one of the few times where I might say, and take a short, because the 2 is going to end up in the front as a coefficient. I might take a shortcut and do one step in my head like that. All right, so now, what's y prime? It's going to be e to the u times the derivative of u. There you go. They might move that trig function in front of the exponent, because usually we do, so they might write it as negative 2 sine of 2x times e to the cos 2x. But there's an example of using your base e, right? Why is e such a nice number? It's the only number in the universe whose height is also its slope. Nothing else does that. Oh, and spoiler alert, it turns out not only is its height its slope, its height is also its area and its slope. It's the only number in the universe that has that property, and areas and slopes in physics and in applications, they mean something. They're really important. So it's why base E, oh, I got a soft spot for base E. Let's do a reciprocal or inverse trig function. So if y equals arc cos of, I don't know, e to the 2x. I'm using the arc notation, inverse cos there. I think the Brits call it arc cos and arc tan and arc sine, which I kind of like better because that I want to treat like an exponent, even though it's not, but it's in the same place as the sine squared and the cos. That I think the inverse notation is one of the biggest mistakes we made in math. And if I was king of the universe for one day, I'd do two things. I'd change the inverse notation, make it an I or a Greek letter or something, not a number, and I'd make 13 months in a day. Each day would be 28 months. That's 364 days. And then New Year's would be one separate day. I said 13 months in a year. Each month would be 28 days. Right? Be a much better calendar. Every month should be 4 weeks long. Monday should always start every month. Alrighty. So, inverse cos. What is the derivative of inverse cos? It's on the back page. Oh, it's also on the front page. So, yeah, it shows up twice. 1 over the square, inverse cos. We have sine on there twice. Cos is on the back page, it looks like. Okay, you know what? Here, never mind. Let's just do this. Sine. There. It looks like, because this is a function, it looks like it's 1 over the square root of 1 minus u squared times u prime. Let's see if we can do this in one step without writing anything down. It's 1 over the square root of 1 minus u squared. What's u? What's u? E to the 2x. So it's going to be e to the 2x all squared, which I think is going to be e to the 4x because power to a times u prime. What's the derivative of e to the 2x? E to the 2x. Oh, times the derivative of what's up there. That's the answer. You'll get that good next year when you do calculus. You'll reach the point where this you'll consider C+, B- level, and you'll do most of them in your head. But part of it is we just haven't given you enough repetition and practice either. You need a semester where they throw several thousand of these at you, and you develop a brain circuit, and you just get good at derivatives. Just do. Trying to look at. Okay, so let's do a tangent line. Pause the video for a second. This is pretty tough. So finding the equation of a tangent line. I guess this graph does go through 4, 1. I hope so. This is what I can't do. The part, finding a point that fits on there, I can't really do in my head. I think this is going to be an implicit differentiation question. So what are we going to do? Step 1, we're going to find the derivative. We're going to find the slope by plugging in x equals 4 and y equals 1 at that location. And then we'll use point slope form to write the equation. This is going to be a lot of work. This is probably longer than we would ask on a test, I suspect. My gut is on your test, it's going to be a polynomial like a parabola or maybe an x cubed, but a nice easy derivative just because, but we can handle this. Okay. The equation of the tangent to the curve at that is, all right. So, again, if I plan my attack, it's going to be y prime, substitute 4, 1 to find the slope at that location. It's a long blink. You going to make it? Okay. It's all good. Okay. Sorry for those of you on YouTube. I got Finn. I missed you. My aim's off. I got boom. Okay, sorry. And then write equation in point slope form. Do they still call it point slope form, or is it called slope point form? They changed the name for some dumb reason. You'll see. Okay? Step 1. Find the derivative. We're going to get a y prime from here, a y prime from here, and a y prime from here. We'll have 3 y prime. That's okay. We'll get them all to one side. We'll factor them out. Still going to be a single y prime. And this is going to be product rule. This isn't. This isn't. And that's a 0. So this isn't too bad. Here we go. Let's take the derivative of x y squared. That's u. That's v. Let's see how good we are. Let's try doing this almost in our head. It's going to be u prime. What's the derivative of x? V, y squared, plus v prime. What's the derivative of 2y? Sorry, what? Gave that away. What's the derivative of y squared? Nope. 2y times y prime. U. There. U prime v plus v prime u. Minus, what's the derivative of 2? Yeah.
Y prime can be written interchangeably with dy over dx.
dy dx, yeah. I find the y prime notation for implicit is a little less cluttered. I find the dy dx is a far superior notation for most applications. I found for this it cluttered up everything. I found it easier to spot the y prime. What's the derivative of 2y? Nope. 2 times y prime. Right? Plus, what's the derivative of 4y cubed? 12y squared. What? Y prime. That equals 6. Let's get all the y primes to one side. You know what? I think this has a y prime, this has a y prime, this has a y prime, this does not. Question?
Would it still be a 6?
Would what still be a 6? Oh, it would be a 0. Thank you. That was dumb of me. Look, I taught calc in 06. It's been a while. Is there a y prime there? And there? And there? How many y primes do I have? 3. How many would I prefer? 1. It would be neat if there was a math 9 operation that I could pull in my back pocket. Y prime bracket 2 xy. It's yx, but I wrote it alphabetically because that's fingernails on the blackboard of my soul. Minus 2 plus 12y squared. That equals negative y squared. Final step. How will I get the y prime by itself? Yep. That's assuming I haven't made these silly mistakes, but you caught the 6, so thank you. Step for finding a tangent line, find y prime. Have we done that? Yeah. Now we actually want to find the value of the slope at that location. We're going to plug in the point that they gave me. So every x is going to be a 4, every y is going to be a 1. Has Mr. Camozzi showed you the clever notation that we use when we're substituting? We draw a vertical line, and that tells everybody I'm plugging in a 4 in for the x and a 1 in for the y. You've seen that? Good. I wish we showed that to high school kids. So much nicer. Okay, that's what that means. It's a very elegant, nice, concise. That's going in there now. Okay. Y prime is negative 1 squared all over 2 times 4 times 1 minus 2 plus 12 times 1 squared. In your head, what's 1 squared? Negative. All over 8 minus 2 plus 12. 8 minus 2 is 6 plus 12 is? So this ends up being negative 1 over 18. What's the slope at 4, 1? Negative 1 over 18. So now I can write the actual tangent line. That follows the template y minus y1 equals m bracket x minus x1. You saw that in the last unit. You realized that's way better than slope-intercept form. Far more flexible. I hate slope-intercept form. I think it's overrated. I really do. Because now I can say y minus, what was the y coordinate? 1, because it was 4, 1, equals negative 1 over 18. X minus 4. And then I would get the y by itself if I needed to. How? More specific? Yeah. Okay. That's the slope of the tangent line. So that's the equation of the tangent line. Then you have the normal line. What's that? Positive 18 over 1, right? If lines are at right angles or normal, that's why we call it the normal force, it's right angles, it's the negative reciprocal. So you flip it and change the sign. And I wouldn't bother putting the 1 there. That's the equation of the normal line. Let's see if we're right. I'm worried here. So, x, y, did you write this? Did anybody write that equation down? Were you following? Okay, I'm going to come back to you in a second. Let's do a little graphing here. Let's go to Desmos. That's what I meant. And what was the equation? It was xy squared minus 2y plus 4y cubed equals 6. Okay. funky little graph. Now, we first of all said that it went through 4, 1. Does it go through 4, 1? It was there. You're seeing it flash. It does. I can't. There. So that's good. Let's try now entering the tangent line. Ideally, that should kiss the graph right there and be exactly matching the slope. So what was the tangent line? It was y equals negative 1 over 18, bracket x minus 4 plus 1. Oh, ooh. That looks good. And the normal line was y equals positive 18, but otherwise going through the same point. Are they hitting at right angles? Aha. It's always nice to see graphically that I think we're correct. That's a really quick summary of pretty much everything. Now, specific questions or topics or ideas that you want me to go over, or we can call it, because we've been going for an hour, and I'm fine with either. Desaiba keeps looking at the clock and doing the periodic table in her head.
I've been up for a long time.
So have I. I was up at 6:30.
I've been up since 5.
Well, I know you are, but what am I?
Oh, well. I actually do have a question.
I have an answer. Yeah. Oh, okay. It's all good. So that certainly for chain rule, implicit, and because that's where kids hit the wall, right? No, I have never seen a calculus kid struggle with the power rule. Oh, move it down to the front, subtract, easy peasy. But you are doing the chain rule in disguise. You were always multiplying by what was inside. It's just because it was an x, it was a 1. So when we broaden it, it's always start on the outside, do that rule, rewrite what's inside times the derivative of what's inside. Repeat. Repeat. That's the chain rule. Implicit differentiation, it's called that because the y wasn't by itself in the first place, so the y prime won't be by itself. You'll have to get it by itself implicitly by doing a little bit of algebra or formula manipulation. Lucky for you, you've done physics, and so you're pretty good at formula manipulation. Did I miss someone? I might have. I can't remember. Who knows? Logarithmic differentiation, trigger. The x is an exponent. Take the log of both sides. The ln of both sides. It's a much nicer derivative to work with. The natural log, the ln. And then eventually you'll get the y. It's going to then turn into an implicit differentiation. You'll end up having to get the y prime by itself. But often you'll have a y. If you're lucky, you can substitute the original equation in for that y. You can do that anytime, but there's implicit differentiation. But usually the y for an implicit differentiation equation wouldn't be by itself in the first place, and so you wouldn't do the substitution. But for logarithmic, it often is. Oh, and then normal line and tangent line. Tangent line and normal line. By the way, now that you can do slopes of curves, there's all sorts of stuff. So your next unit is going to be applications of derivatives. And you'll learn, oh, this is how we used to graph equations before we had fancy schmancy software. How do we graph equations by hand? You can learn a lot by taking the first derivative and the second derivative, because that tells you where the graph is getting steeper, where it's getting shallower, where it levels off, because when it levels off, what would the slope be? 0. So you say, where is the derivative 0? That's where I know I have a slope of 0. Where I have a derivative that's undefined, that's probably where the graph is shooting off to infinity because it's undefined. So there's all sorts of stuff you can do there. I don't know if Mr. Kamosi is going to ask you a bunch of questions about when derivatives do or don't exist, but when don't they exist? When you have one of those cusps, right? One of those points. They don't exist right at that point. When you have a gap, when your graph is not continuous. That's why I did all that stuff about continuity. It was so you could know whether or not a derivative exists. I'm stalling.
No, I got it. My question's done.
Oh, you figured it out? Right. Okay. Yeah.
One question is there's a question on the test that's going to be about finding the equation of a tangent line to a curve.
So that's what we just did. Okay? Now, it won't be this tough. In fact, I'll make up a question that I bet you will be really, really similar. Given y equals 3x squared minus 4x plus 2, find the equation of the tangent line when x equals 5? Sure. See, this one's a bit easier because I can now figure out the y value that goes with x equals 5. I can put a 5 there and a 5 there. I couldn't do that with this complicated equation, which is why I had to go find one that someone had already found a point on for me. I cheated. So you ready? First thing I want to do is find out what point it is. It's 5 comma what? Put a 5 in there. 5 squared is? Times 3 minus 20. So let's do it on a calculator. We would go, okay, 3 times 5 squared minus 4 times 5 plus 2. 57. Kind of yucky, but okay. There's our point. All right. Same steps as before. Find y prime. Evaluate the function. We already did. So, ready? Y prime is going to be what? 6x. Technically times x prime, but that's 1. Minus 4. We're going to evaluate it at 5 comma 57. Well, there's no y here. So really, it's just going to be 6 times 5 is minus 4. Y prime at this point, the slope is 26. So now I can write the tangent line. Minus 57 equals 56 bracket x minus 5. That's the equation of the tangent line. Oh, and then plus the 57 over there. Pardon me? 26? Why did I write 56? I don't know. Apparently I got up at 5. I don't know. Oh, what if they wanted the normal line? I suspect it's going to be a parabola or maybe an x cubed. Because we want to test the concept, but we're not going to push you through something that tough, but we can handle it. Is that all right? Answered your question okay? Yeah. Any more? Okay. Oh, it's from the textbook. Ugh. Please let it be an odd-numbered question that has an answer. No, it's going to be an even-numbered question that doesn't have an answer. Oh, but I got Wolfram Alpha. I can always figure it out from there if I get stuck. Right, and don't be scared to find ways to find an answer on your homework. You can't do it on a test, but there's a reason I give you the answers for physics, right? It helps you work your way backwards sometimes. Or it lets you know if you've done it right. Which one? What are the instructions, first of all? So find the derivative. So I'm going to write that as find y prime because that's less typing. Okay. What's the original function? X to the power of? Okay, x to the power of what? 1 over ln of x. That's it. Is the x sitting as an exponent? It's going to be logarithmic differentiation. Step 1, take the ln of both sides. What's nice is I can now move that to the front. Okay? Now, I'm good with fractions, so I'm going to write this one way, and I'm going to write this a better way. Okay? This can be written as ln y equals 1 over ln x times ln x. You can write it as a little tiny fraction like this, and you saw I hate that I started to write it like this right away. That's 1 over ln x. And why is that so nice? Do you see it? What? The whole ln x's cancel. By the way, we're being sloppy. There's restrictions. X can't be 0. X has to be positive. And so if we were being fussy in university, they would also say, make sure you note your restrictions because we're just being casual. No, they cancel. Well, to a degree. So what I really now have is this. Now we'll take the derivative. What's the derivative of ln y? Sorry, what's the derivative of ln u? I believe it's u prime over u. Is that right from your sheet? Yeah, there it is. They wrote it as 1 over u prime. I would have written it as u prime over u, because to me that looks cleaner. What's the derivative of 1? Okay. Get the y prime by itself. I guess I'd multiply the y over. What's y times 0? I'm guessing maybe the slope right there is 0? I hope. Let's find out with Desmos. So, let's close this, close this, close this. It was y equals, that's a pretty cool graph, x to the 1 over ln of x to the 1 over ln x. Ha! What's the slope of that line? It's a horizontal line, baby. 0. Oh, by the way, with the restrictions that I said, we've got to be careful. X has got to be positive. It's just not going to exist over there. Fair enough, but yeah. Oh, that was nice. Cool. Yeah, the derivative is 0. Not no derivative. There is a derivative. The slope just happens to be 0. Now I'm wondering if I should have been able to spot that easier in my head. There might have been a log trick that maybe I could have simplified this and made it, because if that's what this looks very much like, how high is this? 2.718. This looks very much like the graph of e to the 0. Sorry, that's the fifth. E to the 1. Because e is 2.718. This is a graph that's 2.718 high the whole way. So this must simplify somehow into e to the 1, but I can't remember how. That was kind of cool. That was like a little cleansing derivative sorbet. Could be a thing. I think I'm sensing fatigue, and so I suspect we're starting to approach diminishing returns. So I'm going to hit pause.